our research team. I, Bora Cetin, as the main PI of the project, and Halil Ceylan, Ashley Baz, Junjing Zhang are the co-PIs. From Iowa State University, and Haluk Sinan Çoban is the PhD student, our research engineer, research assistant working with us on this project. And Dr. Lykos, Dr. Edil, and Dr. Ozacak are from University of Wisconsin, are PIs and a visiting scholar working with us on this project. And again, we appreciate the agency members of the NRA and the associate members for their support. Today's outline, we will go about our test sections that were built on MinRAD as part of this project, and what were the objectives and overall idea about the construction process and the field testing and laboratory testing that we are doing, and the summary of what we have learned so far and what we are planning to work on the next 1.5 years, 2 years for this project. And for introduction, payment foundation systems are very important, especially, I mean, it is important both for rigid and flexible payments, but it's very majorly important for the flexible payments, that because these aggregate base, sub-base layers in particular are load carrying sub-layers, and it's very important they are stiff and permeable. And similar thing is required for the sub-base layers, as we all know, and it is also one thing that is necessary for the sub-base layer to provide a good working platform for the aggregate base and asphalt layers. And one thing that with the previous sub-base layers, the permeability was a problem really, and it is very well known the moisture presence in the pavement foundation systems do not help out to the stiffness of the upper layers. So it is very important that the sub-base layers have good drainability. So this map kind of shows the aggregate quality of the materials throughout the United States. And as you can see, the glaciated Midwest, non-glaciated Northern Plains, Colorado Plateau, Wyoming Basin, and Coastal Plain, and Mississippi embayment areas are the areas that has low quality aggregates, and especially in where the NRA states are mainly located, this caused a problem. And for instance, last year, 2 years ago, based on the USGS 2018 report, 1.33 billion tons of virgin aggregates is being used, and more than 3/4 of this for roadway construction. So the demand increased, and the presence of the low quality aggregates causes a increase in the price of these conventional virgin aggregates to be used. So states are looking for alternative materials. For instance, some of these alternative materials are recycled concrete aggregates, recycled asphalt pavements, but now large stone sub-bases are another alternative material to be used in these bays, and most likely the sub-base materials. And large stones has a potential to be used for this sub-base layer, especially for their drainability, drainage capacity, and using less crushing operation, less intense crushing operations, improving the sustainability. The energy consumption decreases significantly, so this makes the material more available, less in a low cost. And one thing, its angularity is decreasing because you don't get intense crushing process that you have in the regular virgin aggregate production or recycled concrete aggregate and wrap production as well. But the lower angularity may contribute to the higher permeability on these materials too, so which is an advantage. One of the main drawback of the large stone sub-base is really there are not enough data that can be followed for design and construction. There are some states mentioning about these large stones, And we mention it significantly in our task 1 literature review report, which is on the MinRAD test data. I have 5 slides at the end of my presentation. If anybody is interested, we can go over them late after presentation is finished. One thing is limitation of laboratory equipment. One of the first thing in any design, DOTs or contractors look for the gradation specs, and determine the gradation of these large stone subbases are not that easy as regular virgin aggregates, because there are large sizes more than 2 inches, 3 inches in diameter, and there are no sieve shakers in a conventional standard laboratory to do that. So part of this limitation, we are going to try to implement this image analysis technique that can be used very quickly. And inconsistent field data, fluctuation of data, one of the studies conducted by Dr. Tutumler, Kazmi et al. 2016, they saw some inconsistency with the field data because of the large voids and the handling of the material because of the size is different. And mobilization of particles is high with these materials. Once you put them, compaction is not that easy, and we will have pictures that I will show. They have large voids, and after you put these large stone subbases and put the base layer and asphalt layer under traffic, they start reorienting itself and keeps moving. And part of our project and going on process, the first goal is really to determine the field performance, and then determine its index properties from the laboratory, especially the particle size distribution and sphericity and angularity and surface texture of these materials are very important. And the third goal is kind of try to come up with design spec for this particular large stone subbases. And we have 6 different test sections, 7 different test sections built with large stone subbases in MinRAD, low volume road test section. It's a 2-lane closed loop, and we are having readings from the outside lane and inside lane of these test sections. And currently the test sections that we have, like I said, 7 different test cells that are built with large stone subbases. The first 2 test cells here are the ones that are built on a clay loam subgrade, and the large stone subbase is built with 18 inches thick material. And then we have 4 cells that are built with 9 inches thick large stone subbases, and there is a triaxial geogrid and triaxial geogrid with geotextile, and another section built with large stone between large stone subbase and clay loam, biaxial geogrid and geotextile, and just another section built with biaxial geogrid for this. And there is one cell 728 that is only with 9-inch large stone subbases, clay loams. The reason why this test section was left based on the construction report is there are too many utilities in this part, so it was not easy to reconstruct this test field. And one thing that is different is with these test sections, with the 18-inch thick large stone subbases, have a class 6 aggregate on top of them as a base layer, and then the other large stone subbases use class 5Q aggregate materials as base layer, and then all of them have 3.5 inches thick asphalt layers on top. And these are the pictures of the materials that were used in this test sections. Clay loam is the subgrade material that is used, and these are the pictures of the large stone subbases, and class 6 aggregate and class 5Q aggregate. And both of these class 5Q and class C aggregates, we didn't complete all the study yet, but they have some sort of recycled materials and some RCA and some rep materials, as you can see from their colors. So they are not purely virgin aggregates. And today's talk will be mainly on the large stone subbase aggregates that we use. And as you can see here, we put the scale for 1 inches, and the large stone subbase aggregates are predominantly much higher than 2, 3 2 inches size aggregates in overall. So during construction process and 18 inches during the construction of 18 inches large stone subbase layers, and actually all large stone subbase layers, there was non-traditional subgrade preparation. So the subgrade was weakened in the beginning to a value that the DCP index should be between 2.5 and 3.5 inches per below the material. And it was loosened and watered to make for the subgrade preparation. And here again, the idea was with the why we have 2 identical test sections here, because one of these test sections were thought to be built in 2 layers instead of one thick 18 inches large stone subbase layer. But due to the construction issues like constructability of these layers in 2 lifts were not really that easy and feasible, so we have 2 identical test sections, one next to each other, one next to another. And then during construction of the 9-inch thick large stone subbase materials, the initial plan was to only have 2 cells with no geosynthetics, as so here, so we can compare the 19-inch large stone subbase layers with the cells that are built with different aggregate materials, and also compare this 9-inch thick materials with the 18-inch thick large stone subbase materials directly. However, there were significant problems with the subgrade. One of them was the subgrade soil pumping. Once the large stone subbase were put on subgrade, the subgrade soil starts being was pumped, moved towards to gaps, voids through the large stone subbases to the surface. And after putting the base layer on top, the significant rotting failures happened during the construction equipment. So all sections were rebuilt, and this time a subgrade. This time, geosynthetics were placed between the subgrade and large stone subbase layers for these 4 test sections that have 9-inch thick large stone subbases. And these geosynthetics, again, let me repeat that reconstructed test section is 9-inch large stone subbases. The first cell had teraxial geogrid, and then combination of triaxial geogrid and geotextile, and biaxial geogrid and geotextile, and biaxial geogrid were put between 9-inch thick large stone subbase and clay loam. And we have this last test section, which we decided to use as a control section with no geosynthetics. And in terms of field testing, we have conducted dynamic cone penetrometer test. Mineral conducted DCP, lightweight deflectometer test, intelligent compaction test, and falling weight deflectometer test. And in terms of dynamic cone penetrometer test, on the y-axis we have the DCP index, inches per below, and on the axis we have them with the SI units, and blue solid symbols are representing the DCP of the subgrade layers. And as you can see, the idea when weakening and loosening the subgrade soil to make sure that these 3 inches per below DCP index were satisfied, then the test sections were supposed to be built. And the x-axis, the red line, red boxes are showing the DCP of the base layer after it is built on it. And as you can see, of course, it is stronger DCP index, lower DCP index than the subgrade layers. And from here, we can observe, in terms of strength, really the thicker large stone subbase test sections have lower DCP index, indicating that they are slightly stronger than the other test sections built with 9-inch large stone subbase with geosynthetics in terms of strength. So lightweight deflectometer test we have followed the ASTM E2835 was followed, and applied stress were 190 kilopascal. And influence depth of the large, it should be kept in mind, the influence depth of LWD is 8 to 12 inches. And these tests are conducted on the aggregate base layer again. So what LWD does, it gives the composite modulus of the entire pavement foundation system. And the LWD deflections, when we look at the entire system, this test sections built with 18-inch large stone subbase had 0.02 inches of deflection, while the test sections built with 9-inch large stone subbase with geosynthetics had higher deflections. As a result of this, they ended up having lower composite modulus values. One thing that we wanted to point out, the subgrade conditions for these 9-inch thick large stone subbases were really, even though they were the same subgrade, the conditions were not really doesn't seem to be the same as this subgrade under this 18-inch large stone subbases. So we have sensor data installed in this test section. So we're collecting that data. We're not there yet, but we will also look into the moisture values of this subgrade and some other characteristics later on after the study to check to see what is going on with the subgrade itself. However, even though we don't see the contribution of the geosynthetics per LWD test results, during the construction, based on the observations, the geosynthetics definitely helped, and rotting did not occur after test sections built with geosynthetics on the base layer. So it contributes, but it's the matter of the range of this LWD test is not really enough to quantify the contribution of the geotextiles on the system. So this was one of another field limitation, actually, to see the measuring the geosynthetics contribution to the field. And I have a few more slides on that we described this more in detail too. And there have been conducted intelligent compaction tests, and here is the preliminary IC mapping were conducted by Ingeos Geotechnics. And then automated plate load testing were also conducted under different stress-dependent conditions, and determine the resonant modulus of the field tests. And these tests were conducted at two different plate contact stresses. The influence depth of the APLT test is higher than the LWD for composite land layer analysis. So these results, we hope that may provide some better information about these large stone subbases. So all intelligent compaction tests were conducted before paving, and we have conducted both composite. So we look into the resonant modulus values of the entire pavement system, and only layered systems, base and subbase, and only subgrade layered analysis from these tests. And again, blue line shows the stiffness of the subgrade layer. And as you can see here, the subgrade layers under 18-inch large stone subbase test sections are stiffer than the subgrade layer of the test sections built with 9-inch large stone subbases, indicating that the large subgrade overall is under these test sections that has 9-inch large stone subbases are weaker. And then we look at the base subbase stiffness from large stone subbases. 18-inch thickness test sections have relatively higher resonant modulus values than the rest of the test sections built with geosynthetics. However, another thing that we see, exactly what Kazmi et al. 2016 and University of Illinois experienced, Dr. Tumler, there is a fluctuation in terms of performance of these large stone subbase test sections. And geosynthetics wise, the triaxial geotextile and triaxial geogrid built 9-inch large stone subbases seem to have a little bit relatively higher stiffness resonance modulus values than the ones built with biaxial geotextile and biaxial geogrid, and geotextile and biaxial geogrid, indicating that triaxial geogrids seem to have slight advantage over other biaxial geotextile, so geogrid and biaxial geogrid plus geotextile test system. And we have Minrad conducted form weight deflectometers, and this is the schematic diagram of this is the picture, and this is the schematic diagram of the FWD tests equipment. So again, we used the influence depth of FWDs at this range, which is on almost the top surface on the base layer of these test sections, and we look at the deflection basin by using all these 9 geoforms to be which help us to do layered analysis to predict the stiffness of subbase and base, or subgrade, subbase and base layers stiffness. And we also look into the composite analysis of the composite elastic modulus of the entire test section by using the FWD test. But in this case, we only use the sensors and measurements at the center, at the plate, at the sensor at the load plate. Again, we did have the FWD analysis that results before and after paving, and again we did the base, subbase, layered analysis, and subgrade layered analysis, and composite analysis, and we have also analyzed the FWD right after it is paved, and we did the asphalt layered analysis. We did the layered analysis to determine the base, subbase, and subgrade, and also composite analysis again. And before paving, again in this time, the subgrade elastic modulus of the subgrade test sections for 18 inches large stone subbase were similar, slightly maybe higher than the subgrade of the test sections built with 9-inch large stone subbase. What elastic modulus wise, it didn't really change much. And the red boxes are showing the base subbase stiffness of these elastic modulus of these test sections. And again, the 18-inch large stone subbases were stiffer than the ones built with 9-inch large stone subbases built with geosynthetics. And another thing that we see, again, another fluctuation within even the 18-inch large stone subbase materials. And as you can see, especially with this second 18-inch large stone subbase cell 227, there is a significant chain variety within the test section in terms of stiffness of this material. But the FWD results are consistent in terms of trend with the intelligent compaction APLT test results, so indicating that our analysis are true. And after paving, we did the same analysis, and again, subgrade stiffnesses are lower as expected than the base, subbase, and asphalt materials in themselves. And from the composite analysis itself. And again, the trend is the same after paving. The 18-inch large stone subbase had higher elastic modulus than those built with 9-inch large stone subbase with geosynthetics. With the composite analysis, we calculated the elastic modulus of the entire system as whole, one system. Again, 18-inch large stone subbases performed better, and large stone subbase, 9-inch large stone subbase test sections built with geosynthetics had lower elastic modulus compared to the 18-inch large stone subbases, and seems like triaxial geogrids seem to have, on average, higher, slightly higher elastic modulus when it is paved, showing that it may have some advantages over other geosynthetic systems that has been used based on these results. And then currently we are working on the laboratory testing of these materials that we have conducted. And we have sieve analysis for the base layers that are used over these large stone subbases, class 6 aggregates and class 5Q aggregates. And we done it for the clay loam material, and as you can see, the subgrade has very high fines content. On the other hand, the fines content of the class 6 aggregate and class 5Q aggregates are 6.3 and 3.2 respectively. For large stone subbase, we are doing extensive imaging analysis, and hopefully by end of April we will have the gradation of large stone subbases. Like I mentioned in the first introduction slide, large stone subbase gradation determination is a challenge. It's a limitation. So hopefully with this tool that we're developing, that limitation will be overcome. And some Atterberg limits for these materials tests were conducted, and here is the Atterberg limits, liquid limit. We had some plastics, not plastics, but liquid limit of the class 6 aggregate was 7.4, but no plastic limit were determined. And this class 6 and class 5 base materials were A1A materials, while class 6 was poorly graded sand with silt and gravel. Class 5Q was really well-graded gravel with sand, and A1A, based on AASHTO classification, makes it very good, high-quality aggregate material to be used in such analysis, such design. The clay soil that we have under these large stone subbases were low plasticity clay. It is classified as sandy lean clay and A6 subgrade material. And again, NA not available now for large stone subbase. We are working on this. Of course, there is. I mean, this should we won't have any Atterberg limits, no plasticity with these materials. Hopefully, we will, like I said, by end of April, we will have these gravel, sand, fines, and all C coefficient values, and along with the definition, like classification of these large stone subbases. And specific gravity and absorption of these materials, a large stone subbase coarse, we can only look into the coarse specific gravity and absorption of these materials. In terms of specific gravity, the large stone subbase specific gravity is higher than the specific gravity of the class 6, class 5 aggregates, indicating that it's heavier material. And in terms of absorption, the absorption characteristics of these large stone subbases is much lower than the absorption characteristics of the regular conventional class 6, class 5Q aggregate materials, as you can see in this table. And currently we are working on the image analysis, and we are doing a 2D scanner, which many Iowa DOTs have access, many DOTs have access on such scanners. And we're doing a 3D particle shape analysis. So what we're trying to do, we try to come up with a stereophotography tool. By taking just 2D pictures, you can predict the 3D dimensions of these materials. And we will validate this stereophotography analysis with our 3D scanner scanned parameters. And this is the stereophotography station that we developed, that we built. So we have camera on top here, and we put the large stone aggregate, the large stone subbase materials down here, and our camera slides. So for a stereophotography analysis, you need to take the same picture of the same material with at least 2 different positions, so you can create that 3D model. So in our analysis, we take pictures, one at this left edge, one at the right edge, and one at the center, so we can get a more reliable stereophotography analysis. And then this is one of the examples how we predict the 3D dimension of these aggregated limestone. On the y-axis and x-axis, the camera reads the inches of these materials, and in the z is giving the height of a certain point of the rocks. As you can see, we don't have cubes, as we all know, we don't have cubic, perfect cubes or prismatic aggregates, so their thickness changes. So these we have this colored scale. So the red, dark red means this part, this portion of the aggregate material is that 2 inches thick, while these sides are not that thick. So this gives us an exact 3D dimension of limestone subbases. And how we validate this stereo photography, we take representative samples and do 3D scanning through the Aeon scan scanner. And then we validate our stereo photography tool, and then use that by taking just picture of the material and determine the aggregate sizes. And this is kind of some examples of the 3D scan side views and top views of the same aggregates. And this is the image analysis are being conducted at Iowa State University as of now, and the University of Wisconsin-Madison are conducting the permeability and water retention characteristics curve for aggregate materials and subgrade materials. With the this is a typical permeometer with constant head reservoirs for headwater and tailwaters that are used for aggregate base materials. This is not applicable for limestone subbases, and we will Wisconsin will conduct the permeability test on the limestone subbases after we are done with our image analysis and all that. And these results are showing the hydraulic conductivity conducted on the base layers, class 6 and class 5 Q materials, and the clay loam material at certain density values and moisture content values. And on average, as you can see, the hydraulic conductivity permeability of the class 6 and class 5 aggregate bases are between 10 to the minus 2 and 10 to the minus 3 centimeter per second, while clay loam hydraulic conductivity is close to lower than 10 to the minus 6 centimeter per second, which is expected. So what we have learned so far from our research on the limestone subbases, definitely during construction stage, impracticality of two-lift construction for 18-inch limestone subbases. It was just not feasible. And subgrade soil pumping due to large opening size of limestone subbases were observed. And once you put the base layer, rotting occurred. So these were the problems. And for instance, with the 9-inch thick limestone subbases, these two were overcome by putting geosynthetics. And one of the, I think however, the challenge with this is quantifying the contribution of the geosynthetics in terms of stiffness and strength gain were not feasible. The reason for this, the current test methodologies, LWD or APLT, automatic plate load test, or falling weight deflectometer test, the load that is put on the test sections are not really is not enough for geosynthetics really to start showing their contribution. So different test methodologies, maybe heavyweight deflectometer test methodology that is used usually for the airport pavements, may be used to observe to quantify the impacts of geosynthetics on the stiffness and strength of these test sections. And especially with 18-inch thick limestone subbases, we see significant variation in the stiffness, even within the each test cell in themselves. And this could be compactability is a problem of limestone subbases. This could be related to this. And stiffness of class 5, the test sections built with class 5 Q aggregate and class 6 aggregates were lower than overall than the class 6 aggregates. Again, the speculations currently with the information that we have, hopefully we're collecting more data with MinRAD. Hopefully we will have more information about this later on. Instability of 9-inch large-stone subbases, as we observe with the 18-inch large-stone subbases. Insufficient compaction of class 5 aggregate may contribute to the overall composite analysis. And we have some data that shows that we are working on the analysis of that, so it may be related to that. All right. And test what we have learned. The currently specific gravity and absorption for large stone subbases can be done, but you can't do traditional gradation. You don't need to do Atterberg limits because it's non-plastic, or Proctor compaction test won't work for large stone subbases. So gradation has to be determined via image analysis. So we are working on that tool that will be available. And one thing that we learned, which is expected, I guess, by the local DOTs too, class 6 and class 5 Q aggregates, these classifications based on the gradation, and these materials are allowed some recycled materials to put in. And class 6 has some reps visually that we can see, and we are working on the asphalt content to determine how much that we have in class 6. And class 5Q base aggregate has some RCA. We can smell really the cement out of this. So these are some of they are not really virgin aggregates. They have some recycled materials in it. And we learn, as expected, I mean, subgrade material has much lower hydraulic conductivity than those of aggregates, and we hope to get large stone subpermeable for large stone subbase materials. And the future thing, we are currently working on the asphalt and cement content of the base layers that are used on this study. And in addition to the gradation, the size of the large stone subbases and other aggregates, we were going to look into the angularity and sphericity of these materials. And we look into the hydrophility and hydrophobicity of the RCA and reps. Rep is we want to learn how hydrophobic our rep materials is and how hydrophobic the RCA materials and other conventional aggregates used. And we continue to collect the data from MinRAD on elastic modulus values and temperature and moisture data. So especially this temperature and moisture data will be very useful to tie that into the elastic modulus values collected from the continuous FWD results. So we can see how that if the test sections built with geosynthetics have higher moisture conditions, so that contributes to this lower stiffness and strength values. Having said that, this is the end of the presentation. Be happy to answer any questions. And Bill, Tanser, I don't know if you're there. Anything that I missed, please feel free to chip in.
Well, thank you very much. We've got plenty of time for questions. They will start here in the room, and then Bob, I don't know if anybody. So online, if you're start sending some questions, be great. So any questions here in the room? I'll throw one out to begin with then. On the imaging, what's the maximum size rock, I guess, that you could image with your couple of techniques there?
Probably the size of the 3D scanner is probably won't go beyond 6 inches, John. So maximum 6 inches, I think we can, 6 to 8 inches, I think we can go. Actually, for 3D scanner, that's the thing, but for the stereo photography, we can go whatever size that we want it to go. Because, for the stereo photography analysis, you just need to take the picture of the rock from the top and from some other angle. So there is no limitation in terms of really the size that we will have to use.
We have a question online asking when the test sections were constructed.
In August 2017, if I'm not mistaken. John, Dave, please feel free to chip in, but my understanding it was built in summer 2017.
Correct, yes. Well,
What did they shoot that through was the asphalt on when they did this?
for the imaging.
Yeah.
I think the question's about another follow-up on the imaging. If you can just louder.
Did the stereo photography there, did you do any of that through the asphalt? Can you do it through the asphalt?
No, we didn't do that through the asphalt.
Can it be done through the asphalt? No.
No. No, we did not. We just started doing the stereo photography on the, recently, last few months. We didn't do any imaging during the construction process at all. Did I understand the question right, or?
Yes.
Okay.
We have another question online. Now that there have been out there a couple of years, do you have any early performance observations, distresses, rutting, etc.?
Not that we're aware of. Actually, we were gonna, since now we had a harsh winter, we were gonna give a visit late March or early April to do that. Before the winter, there was none, and it was a very tough winter, so we waited for the thawing season, and now it starts warming up. We will check on that, but before winter, there were none. John, Dave, if Dave is there, did you guys see any rotting or significant fatigue cracking on that?
Not that I'm not aware either of much difference between these test sections after the first year, essentially. So now that maybe we'll see something now and 2 years later. And
Yeah, but
watching it for the next several years.
Yep. So none so far.
Is there any concern about soil migration from the base to the subbase, and would that have any mechanical effect?
Great question. Yes, there is a concern with that, especially with 18-inch large stone subbases. So I talked to Dave on this, and so we will try to do some maybe additional. I will talk to Dave and John about this too. They done initial GPR test that we will collect it and try to analyze it ourselves right after construction. And maybe if possible, if we can do another GPR scan on these large stone subbases, especially the 18-inch thick ones, we may be able to see that if soil migrates at the bottom of the large stone subbases. So yes, there is a concern, and we will try to quantify it through ground penetration radar data. John, Dave, is that possible? If sometime in summer or late spring we can do another GPR scan?
Well, I guess most likely certainly it's possible. I think we'll talk about it and figure out what the availability of the equipment, I guess, but it seems likely it could be done.
Yeah. Or we can do it in the fall too, wait a little bit more, there is a concern there. With geosynthetic test sections, that concern is minimized, especially with the GeoGrid, Geotextile combined test section. But yeah, concern is there, so we will try to quantify if the GPR is available, and we will do the analysis and all that. So.
And I guess eventually, when we tend to do forensics at the end of these projects, and so at that time, then we'll get, when we actually get in there and look at it, we'll have another chance to see if there's how much migration there has been or hasn't been.
Yeah, that would be the best. It will be really quantitative visualization of that, quantification of that. So
we've got a few questions online, and a couple of them are GeoGrid questions. The first one is, do the trucks run on the low volume loop year round? And yes, that's true. We do have the truck going year round. But the other two questions are GeoGrid. The first one is, what was the opening size used on the GeoGrid? And was there any consideration for including a layer of GeoGrid at the mid-level of the LSSB?
Let me look at the data that I have here. The second question, John, I wasn't there when these test sections were built. It would be better, of course, to put between the GeoGrid between the large stone subbases or any base layer. That would definitely improve the stiffness. But was there a thought that GeoGrid was supposed to put GeoGrid at the middle of the large stone subbase, John?
Well, this was not. I mean, this particular study did not include geosynthetics at all when it was proposed. And so what happened was, when we tried to build the 6-inch or the 9-inch large stone, it really was not feasible. So then we had to do what would have to be done on a regular project, is find a way to move on. And so the idea was just to create a construction platform. So that's why the grid and the grid end textiles were put on top of this very soft subgrade clay. So it wasn't, we didn't, certainly it would be additionally beneficial to put more grid halfway up. But this wasn't a grid study to begin with.
So we have the dimensions for the geogrids. The question, the biaxial geogrid aperture dimensions were 46 millimeters, the opening size, and for the triaxial geogrid, the rib pitch dimension was 60 millimeters opening. Yep. And this is also in the report, in task 3 report that is uploaded online. Any details regarding the materials that are used are there too. So it also other isotropic stiffness ratios, ultimate tensile strength of these geogrids and geotextiles can be found there. And the apparent opening size of the geotextile that is used with geogrids was 0.15 millimeter.
Any more questions here in the room? Any ESLs in the line? Okay, well, I think sounds like we're probably pretty well covered it. Thanks again, Dr. Cetin.
Anytime.
I don't know, Bob, do you have anything else from a, okay.
Nope, we're good.
I guess we're done. Thank you very much. Have a good day.
Thank you very much, everybody. We really appreciate all your time, and feel free to contact us with any questions.